Hey AP Calculus. So this short video is going to be an extension of our summation notation notes that we talked about today, but we're going to look rather how would the summation notation be different if we used left rectangular approximations as opposed to right. So to give us a little perspective here in drawing this, we know that the delta x in this case is still going to be equal to 2 as we did in the previous example up top here. So just as a recap, we have the delta x equal to 2. We are going to write the right Riemann sum approximation method here. And just to remind ourselves what that is, it's I1 up to 4 of f of 1 plus 2i times 2. So we'll leave that there and come back and talk about it in a moment. But here's what the visual is going to look like, just to give ourselves something to look at. And once we have these drawn, okay, the big question is going to be now, for each of these rectangles, is what is that x sub I going to be in this case? So for example, in this first rectangle, we're taking f of 1 and multiplying it by 2. Then we're taking f of 3 and multiplying it by 2. F of 5, multiplying it by 2. F of 7, multiplying it by 2. So kind of like what we did before here, I'm going to look at the I values. I, again, are the number of the rectangle, right? So the first rectangle, I is 1. The second rectangle, I is 2. Third rectangle, I is 3. Fourth rectangle, I is 4. And what does that translate to? Well, that translates to being x equals 1, meaning we're plugging 1 into the function. We're plugging 3 into the function. We're plugging 5. We're plugging 7. So in terms of developing a formula for this, we have to think of something that's going to work for all of this. So we're going up in odds, and typically odd numbers can be found by taking a number like I, an index value, multiplying it by 2, which gives it an even value, and then either adding or subtracting 1. So if we were to use that, okay, if we were to use that situation here, we would essentially be doing 2i, so we would double it. And then in the case of all of these here, if I double 2, it becomes 4. If I double 3, it becomes 6. If I double 4, it becomes 8. So to get to the desired x value, we would just subtract 1. So we seem to be getting 2i minus 1. Now, that doesn't necessarily actually help us here, because what we're trying to do is look for some sort of a formulaic approach. So like for the right Riemann sum, what we ended up noticing is that it always became the a value plus the delta x value times the index, or I, okay? We don't necessarily have that in this situation here, but what we can do is we can rethink how we can write this formula up here that we learned in terms of going 1 unit to the left. Think about that for a moment, because notice how the 3, 5, and 7 that we learned earlier, okay, that is just 1 unit shoved further. It's almost like a transformation of sorts, that the rectangles were shifted 1 delta x value to the left. So one way that we can think about this is I want you to consider this as an option. What if instead of looking at 2i minus 1, which is the formula we came up with here, what if I considered instead 1 plus, so looking at the same one, 2, but then the I value, the index value, is just simply getting shifted over 1 unit, meaning we're subtracting 1 from it. Take a look at what happens when you simplify that. You still get 2i minus 1. So the moral of the story here is that what we can do is for a left Riemann sum is that we can essentially perform almost what we think of as a transformation to this, where we are just moving the I value and subtracting it by 1 value, 1 delta x value that is, in order to create the summation notation. So that summation notation would go from I equals 1 to 4 still, because that's going to be 4 rectangles. The function will now be determined by the formula 1 plus 2 parentheses I minus 1 times the delta x, which is 2. There's one other approach that we could do to this that we also could be accepted here. And the reason I'm showing you these different methods is ultimately on a multiple choice question, you need to be able to recognize this in a problem. So if you see this minus 1 in here, this I minus 1 in parentheses, that's maybe referring that it's a left Riemann sum approximation that you're looking at. But if we look up here, another way that we can write a summation notation, and depending on your background knowledge on summation notation, you can write summations of things in different ways, as I've just shown you. Another way you can do it is keep in mind that the index value we're choosing for it to start at 1. But what if instead I made the index value move 1 ahead, or sorry, 1 behind? So instead of starting at 1, if I started it at 0, because if I started it at 0 and I plugged 0 in to start, I would get f of 1. If I plugged then I equals 1 in, I would get the 3 that I'm looking for. If I plugged in 2, I would get the 5, and if I plugged in the 3, I would still get the 7. So another way here that we could write this is we could start the index at 0 instead and go up to 3. That's still showing 4 rectangles because 0, 1, 2, 3 is 4 numbers. But then we would be able to use the exact same function notation for x of I that we used for the right Riemann sum. So both of these summation notations would be accepted as an approximation for the left Riemann sum. Now I want to ultimately mention one final item on this video before we wrap up, and that's if you throw a limit on either one of these, it's still going to equal the exact same definite integral, because even though you have a left Riemann sum versus a right, when you are summing up an infinite number of these, so I'll just use the top example because for time's sake here, it's less writing. If I write this out here, 1 plus 2i times, oh, well, I guess we have to remove all the n's, so keep that in mind now. So we need to go back and change some of this. So our delta x, remember, was, let's go back up to the beginning, it was 8 over n, it looks like. So just need to remind myself of that. 8 over ni times 8 over n. This is still going to equal the same definite integral that we had from earlier. So it's going from 1 to 9 of f of x dx. So that doesn't change the definite integral part. It just may change again if we were trying to write a Riemann sum with a left rectangular approximation. We obviously could go into this conversation even further by talking about midpoints and other types of different Riemann sums, but ultimately, right Riemann sum is the number one form that you want to be able to familiarize yourself with, and there could be a rare occurrence on the AP exam where maybe they talk about left Riemann sum approximations written in summation notation. Hope this video was helpful for you guys, and please reach out if you have any questions. Thanks.